Welcome everyone to our Wednesday, April 3rd paper reading. The paper we are going to read has a provocative title, The Unreasonable Effectiveness of the Deeper Layers. I suppose it's a play on the word in our field. People often remark at the unreasonable effectiveness of mathematics. No one seems to understand why very simple mathematical ideas have such profound implications. But this paper uses that to make a converse statement. Now, a little bit of a background. If you recall, these days, bigger is considered better. We all understand the neural scaling laws and words like chinchilla, optimal, and so on and so forth. The gist of it is that if you have a lot of data and you have a lot of compute accessible to you, then with those two preconditions being fulfilled, you often find that as you scale the model up, they gradually, not suddenly, they develop new abilities. At one time, people believed that these new abilities emerge suddenly at a certain scale, but now we do know that it isn't the case. These emergent abilities are a mirage, and they're both a mirage and not a mirage. They do come about. These models, they begin to get better at things like arithmetic as the scale of the model increases. As you go, for example, from billion to 10 billion to 100 billion parameters, they begin to do things. Gradually, they improve at things that you wouldn't, that they weren't able to do at much smaller scale. So bigger is better has been a sort of a catchword in this phrase. People talk of whether 300 billion parameter model is enough, or whether 70 billion parameter model can do it, or whether 7 billion parameter model can do it, or 2 billion parameter model can do it. And in the mix of all of that, all of these practical considerations, when you look at models that you can actually host or load or train or fine tune on reasonable hardware, let's say, when it comes to 4090, what most people have access to, NVIDIA RTX 4090, then of course it seems almost hopeless that you'll be able to fine tune things. But over the years, the situation has been getting better. For example, the parameter efficient fine tuning methods, they have made it possible to fine tune models that you wouldn't have thought possible on much smaller hardware, even onto 4090 or a few 4090s put together. You can do that. Things like LoRa and quantized LoRa. So there are essentially two ways we know. You can quantize a model, go from 16 bits to 8 bits to 4 bits, and so forth. And now there are even talks of going down to 1.58 bits or something like that. Without huge loss in accuracy. Now, it depends upon how you look at it. Some people would say that no, the results get pretty unsatisfactory once you go down to, once you quantize very heavily. Others say no, that for certain tasks, it does continue to be reasonably good. So quantization is one axis. The other is when you're fine tuning it, you could use obviously the model. You could take a smaller model and fine tune it for using LoRa and quantize LoRa as needed. That's another thing. People also look at distillation of a model. They take a model that's really capable and you go through the process of distillation as student teacher, the bigger model being the teacher and the smaller model being the student, and it learns to imitate or learn from how the teacher answers questions, for example, or produces the tokens. Now, when it comes to distillation, you can have black box and white box distillation. So, for example, if you can see the logits coming out of the last layer of the teacher, then the student can try to replicate that logic distribution over the words. If the model logits are not visible, it's a closed box or black box kind of a teacher-student distillation. In that case, the student simply tries to replicate the tokens being produced by the teacher. Right? So you have teacher-student as one way to create smaller models through distillation. So there has been various efforts to go smaller and still preserve the power of these models. Now, this paper I felt interesting. It just came out about a week ago. And what I found very interesting is it asks a question that many people, I suppose researchers are beginning to ask, where exactly is the real power of the LLMs and which of the layers it is? Now, there has been a body of research that shows that when it comes to uh, decoder GPT-based models, the earlier layers seem to be more important, far more important, and they are central to understanding it. There is some hunch that perhaps the later layers retain knowledge. They sort of are parametric memorization of the input in some sense. Right? They can keep that. At this moment, I don't think that there are very definitive statements. There are different bodies of research, uh, different studies showing, giving clues to what might be happening. We don't, as of today, I don't think we have very definitive statements. So in that same journey, in that same pursuit of clues on what these models are up to internally, this paper studies in particular GPT-like models or decoder-based models, and it takes a few of those. And in particular, it takes Llama, 70 billion parameter model, and then it takes a few others. And then it says, let's look at these models and ask, are there some layers that we can theoretically take out without significant loss of accuracy? And then suppose we lose a little bit, can we sort of compensate for it or heal the removals? If we surgically remove some layers, can we heal the removal by throwing in some LoRa or Q-LoRa fine tuning? Right? So you subtract some, you lose a little bit, but you try to regain it by fine tuning the model back on the data and seeing if you can regain it. And the remarkable result that they find out is that you can do that. You can actually take a large language model and start strategically hunting for layers that seem to not do much, right? That seem to be more or less an information transition. They just transit or they act as conduits of information from the previous layer to the subsequent layers. And if that is true, if that really is true, then of course they become prime candidates, a block of those layers, let's say a stack of n layers, they become maybe 10 layers, they become prime candidates to just remove because all they're doing is transmitting information from, let's say, layer 11 to layer 21, hypothetically. Right? So that is what this paper is about. We will read through the abstract. Now, interestingly, this paper is obviously, you can see the collaboration of a lot of powerful AI research houses. You have MIT here, you have Meta, the FAIR Group, University of UMD is, I suppose, University of, what is it? I don't know, Maryland, University of Maryland, yes. Meta, yeah, Cisco and Zyfra. So let's read this paper. We'll start with the abstract. So in the spirit of paper reading, I'll read through the paper. If you feel that you need to ask a question, please feel free to. We'd like to keep it very interactive. But remember that you are on record. If you feel that you would like to have more open-ended questions, keep it for the very end. If you feel you would like to ask some questions but not on record, once again, keep it for the very end, and we'll take it after we are done with the first part of the session. So I'll read the abstract. It says, we empirically study a simple layer pruning strategy for popular family of open weights pre-trained LLMs. So what are open weights pre-trained LLMs? For example, llamas and all of these. we call them open weights because we know the architecture, we know the weights, but it isn't quite open source in the sense that all is not known about them. We don't have the data with which they were trained, and what how did they decide on the hyperparameters and so on and so forth, what hyperparameters tuning they did. So to train a model takes a lot, and to not reveal all the techniques that went into pre-training a large language model or a foundational model is sort of a compromise on the spirit of open research. So, well, that happens to be the reality today. A lot of these, well, of course, a lot of people, a lot of companies, they obviously don't give you their models. They're commercial, especially the big AI houses don't tell you what the model is, or they don't give you access to the models, except through API, monetized API. Then the open source community, there's been a bit of an unfortunate trend where you notice that a lot of the models are released so-called open source, but they're not truly open source. They are open weight models. So that speaks to the peculiar word that you don't see anywhere else called open weights. So these are open weight LLMs. And what these people find is finding minimal degradation of performance on different question answer benchmarks until after a large fraction, up to half of the layers are removed. So this is a critical thing. What they're saying is that the performance essentially, like if you take some axis, the number of layers, let's say the number of layers removed, a percentage, let's say percentage of layers removed, because different models have different number of layers. Some models, big models, are very, very deep. But let's look at the percentage of layers removed. Now, the question is from where, from which end of the architecture do you remove them? That question will come to. But if you take some measure of performance, let's say accuracy or whatever it is, I'll just use the word performance, model performance, in a more general sense. And I believe they look at accuracy here. So what they find is that, and this is the crux of what they find, is that performance more or less remains like this. It's a simplified picture that up to a certain threshold, performance does not degrade if you keep pruning the layers. Or even if it degrades, well, if it may not be exactly like that, but it's a very, very, very slow degradation. And then there is a catastrophic, there's almost like a phase transition, after which the degradation of performance is substantial. But the remarkable thing they point out is that up to a certain limit, let's call this limit a certain percentage, right? A critical percentage, you can go on removing removing layers from the model. Sometimes you can remove almost half the up to half of the layers are removed, and this is the finding is the remarkable finding. Minimum degradation of performance on different question answer benchmarks until after a large fraction of the layers are removed. So isn't it quite remarkable and something worth observing that sometimes this is almost 50% of the layers and the model still continues to do just as well. So that begs the question then that have we stumbled upon, these researchers, have we stumbled upon a very effective process of shrinking the size of a model? Right? For example, distillation is one, LoRa, the perf methods, in particular LoRa, another, quantization is another. Is this something new that we can harness going forward? So that's the question. Let's look at it. To prune these models, we identify the optimal block of layers to prune by considering similarity across layers. And then to heal the damage, we perform a small amount of fine-tuning. So one way to look at it is, suppose you have a network, you have a very large layer. You know that information travels in this direction. So every layer, L plus 1, depends on information coming from the layer L. Right? So you cannot just like it has certain level of dependency on layer L. So if you go and suddenly excise a certain number of layers, one would imagine that it has done some damage. Yeah, go ahead.
Is this an implementation of the laser paper that Shalini went over?
It's a different thing. They don't specifically use those techniques. It's different. Yeah. So it is actually a very simple idea. It just says let's prune. And so it doesn't put it in a larger context at all. It just says, we found that if you prune, you get good results. And that's what it is. And that's what we are focused on. We say that if you remove this, then inevitably you might have done some damage. It turns out that you don't do damage in the till for small percentages of things being removed. But after a certain while, you start taking damage. So think of it as surgery. What you need to do is you need to fill it in. Right? This damage you can sort of heal. They use the word heal by fine-tuning with LoRa to LoRa. Because they do all of these experiments on a single A100, a single A100 in our AI field is supposed to be a fairly modest amount of GPU available. Typically, like if you are in university settings or things like that, that's sort of the de facto standard. You'll get access to, or you will have a budget to reserve yourself a A100 in the cloud and play with it. So in particular, we use parameter efficient fine-tuning methods, specifically quantization and low rank adapter, QLoRa, such that each of the experiments can be performed on a single A100 GPU. Now, just as a quick recap of what LoRa is, or QLoRa is, what are the two big ideas of a QLoRa? Suppose you have a base model, a pre-trained model. So QLoRa recap. It's based of two big ideas. So first is the LoRa and then the Q part, pre-trained model. Let's call it M naught. So suppose you have a model M naught. It has its weights and biases. Right? What you do is you keep it frozen. You don't alter it at all. You just load it. Now, loading a model in a frozen form is a lot more feasible on low memory GPUs than opening up the weights for training. Because let's say that you have an input X and you want to fine tune this model. If you open up all the weights, then let us say that the number of weights or the number of parameters is P, right? Then for all the parameters, each of the parameter, you will have to store its gradient, the gradient of the loss. So let me just take it as a weight. That parameter is a weight. Or let me just say theta, some parameter. You'll have to store theta, isn't it? You'll have to compute the gradient of the loss with respect to theta. And then you have to add a few more things. And before you're done, you realize that you have a multiple of the amount of memory that you need is not just the memory required to train them, just to store the parameters, but you have a lot of additional gradients and so on and so forth that you have to store. And for example, if you use Adam, then you have the gradient square, right? G square, let me just use the word G square, gradient. You have the G square terms also stepping in. So all of it put together, this already becomes three times number of parameters that you are storing. And this begins to look infeasible, because if you take a let's say you're looking on a 4090 and you're sitting upon a 24 GB. On a 24 GB, let us say that you have, first of all, on a 24 GB, you can load a 7 billion parameter model, because 7 billion would consume about 14 GB of VRAM, plus some overhead, Let us say that this will come to about, give or take, 17 GB, let's say. You can run inferences on it. You can run the forward pass inference on it. X goes in, Y hat comes out. Right? Why? Because you're not having the gradients and you're not having the quadratic terms that you are also having to store for the Adam W optimizer and so forth. It's just doing the forward pass. But the moment you open up all the weights for optimizing, for fine tuning or for learning, then what happens is it becomes 3 times. If you look at it, so suppose 17 times 3 now begins to look pretty bad, right? Uh, not feasible anymore. More. And so you can't fine tune even a small model, a 7 billion parameter model on your 4090 or something like that. So the way out that people found was very clever, actually. They said, leave this model M naught frozen. Don't touch it at all. And instead create a low rank A, B, take two matrices, A and B. And so what you do is your input goes to this, it produces its particular output. Let me just call it the output Y naught hat of X. And you pass it through this, and it produces its output, LoRa. Let me just call it LoRa. Y hat LoRa of X. And what you do is you concatenate these two, you add these two results to produce your final Y hat. Right? Now, if you are clever about it, and the rank that you put of this matrix is very low, typically, let's say 4 or 8 or something like that, then what happens is, even if your initial, so just for the sake of argument, let us say that this was 1,000. Let's say that this is 100. And normally, 100 times 100 would be 10K. 100 times 100 is equal to 10K. On the other hand, 100 times 4 is just 400. And then again, 400 times 100 is again another 400. So coming up to a 800 number of weights that would be there in this matrix, right? Which is a whole lot smaller than 10,000. So what happens is that if you open these weights, 800 weights for training, you make them trainable. So in other words, for these weights, let me call them LoRa weights, they're small matrix weights, like WA, WB, if you say, then even if you're doing the gradient of the loss with respect to WA and the G square, the gradient square, etc., all these terms come in, we are still looking at 800 times 3. Right, that is a 2400 and times 2 for 2 bytes. Even if you do 16 bits, but typically you quantize it down to, and the Q, even then you're looking at a fairly small memory utilization. Right? And so you can train or fine tune using the LoRa approach. Now, further to LoRa is the Q-LoRa part. Q-LoRa says, let's not do it at full 16-bit precision. Let's decrease the precision down to 8-bit, 4-bit, etc. And the way to do that is, we happen to know that the weights, all of the weights in a model, we leverage the fact that they tend to show a normal distribution. So in other words, instead of doing equal size quantization or bucketization, we can do a quantization that leverages the fact that data or weights, sorry, parameters have weights have a normal distribution. In other words, they are just fluctuations around zero, small fluctuations around zero. They're small values, positive, negative values. Most of the weights are rather relatively small. So then you can do a distribution-aware quantization of this, and that is the Q-LoRa part. So that is about the LoRa and Q-LoRa as a refresh. So what do they help you do? They help you fine-tune a model on relatively modest hardware. And what they are saying is, when we excise a whole bunch of layers from the model, what we will do, we will lose something. But after losing it, we can sort of regain things by putting on the side an ancillary LoRa adapter, Q-LoRa adapter, Q-LoRa, well, Q-LoRa is redundant. LoRa A in LoRa stands for adapter. You can put a Q-LoRa on the side and fine-tune it again with the data and restore or heal it back to its original accuracy or original performance. That's what they're trying to say. Right? So that is the gist of what they're saying, and so we'll do that. From a practical perspective, so what they say, in particular, we use parameter-efficient fine-tuning methods, specifically quantization and low-rank adapter, QLoRa, so that each of our experiments can be performed on a single A100 GPU. From a practical perspective, these results suggest that layer pruning methods can complement other parameter-efficient fine-tuning strategies to further reduce computation resources of fine-tuning on the one hand, and can improve the memory and latency of inference on the other. From a scientific perspective, the robustness of these LLMs to the deletion of the layers, implies that, and this is, I think, so while there is a practical benefit to doing this, scientifically, there's a more important statement here. From a scientific perspective, the robustness of these LLMs to the deletion of layers implies either that current pre-training methods are not properly leveraging the parameters in the deeper layer, right, or of the network, or that the shallow layers play a critical role in storing knowledge. It means that the initial layers, like either you say that we are not training them properly, a lot of the layers are left unproperly trained or unutilized, really, or the other is maybe there is a fundamental process by which the shallower layers play a far more critical role, and after that you reach a point of diminishing returns. Right? That's one way to look at it, that you may reach a point of diminishing returns. Now, why is this valuable? So we'll read now. Over the last few years, large language models have evolved from mere research artifacts into useful products. To a large extent, so this is all preliminary. Right? The important thing it mentions somewhere is that, see guys, our model spends most of the flops. Yeah, this statement is very crucial that it mentions, and I will highlight it in a different way. See, it takes a lot of time and effort to train a model. Right? But at the end of it, that model is deployed in practice. And it is going to spend a whole lot more time, orders of magnitude, more time performing inferences. That's a crucial observation. You build models so that they are used, and then they are used for a very, very long time. Think about any model, like for example, the GPTs or the BERTs. They have been pre-trained once, and after that, people have been using it for inference for all over the place. So this is inarguable. So therefore, the pre-training of LLMs requires not only considerations for efficient and compute optimal training, but also requires inference awareness. Means you should be aware that at inference there's a heavy cost if you make it too big. What about models that have already been trained? Beyond the training considerations indicated by neural scaling laws, there are also numerous post-training techniques for reducing the cost and time of fine-tuning and then inferencing LLMs. In particular, so we are familiar with these things. In particular, you can take a pre-trained model, quantize it, attach, do fine-tuning using LoRa, and so forth. So it's a review of the very familiar ground. And then, building on that combination in this work, we study a very simple pruning strategy using an open weights LLM. In particular, we develop a method that uses the similarity between representations at different layers, etc. So I won't repeat it because I have already explained that. But I'll go to the main idea that they say, which is that overall, we hope you take these 3 bulleted points with you. the model's memory footprint and inference time decreases linearly with the number of removed layers. That is a no-brainer, right? You remove layers, its footprint and inference time, the number of computes that you have to do will decrease. This makes layer pruning a powerful tool, especially if the model's performance is robust to dropping layers. So in other words, if you drop a layer or two or three and performance doesn't go down, then obviously you have less memory footprint and your inferences are faster. That's the first point. The second point they're making is that all the efficiency methods, pruning, parameter efficient fine-tuning and quantization, can be effectively combined with each other, which again, because they're independent methods, you can combine them. Thus, in this work, each experiment was performed on a single A100 GPU and is easily accessible to the open source and academic community. So the idea is that in the open source community and academic communities, we do have access to A100s. We can go to the cloud, reserve it, pay by the hour, and so long as it doesn't go on running, it finishes in finite amount of time, we pay a small price. The robustness of models to removing the deeper layers, the sharp transition in performance on downstream knowledge tasks, e.g.
The recording stopped for some reason.
Kate, that was not us. That was somebody in the audience who was using their otter to record.
Okay, never mind.
We wouldn't care about that. The robustness of the model to removing the deeper layers, the sharp transition in performance on downstream knowledge tasks, e.g. Example, the MMLU and the bool cube. Now, what in the world is MMLU? It is a massive multitask language understanding benchmark. It basically manifests itself as a lot of multiple choice question answers, and it's a QA sort of a task. And then the bool queue is a more reading comprehension centered benchmark. It sees how well the machine can understand the text that it is reading. Right? So these are downstream knowledge tasks.
Asif, we don't see the YouTube link anymore. So it's, I think, our thing that has stopped.
Are you sure? Okay.
Yeah.
So in that case, let me pause and I'll repeat.
Something happened, so I cannot see the link anymore.
All right. Which start? Okay, we can restart. Thank you for pointing that out. Let's go and see what's going on. It does say live. Yes,
yeah, we're live on YouTube, Asif. I can see it.
Okay.
I think Asif recording has been stopped. That's why.
Recording is stopped. Okay. So we'll start another session. Let me kill this entire thing first and start a new Chrome.
Asif, I see you live on YouTube. It's going fine.
So recording is stopped. Okay. So we'll start another session. No, recording is very much in progress, it seems. Let me kill this entire.
Yes, it is.
Start a new Chrome. All right. Sorry for the interruption and the confusion. Let's continue and march on. So the last point that they make is that the robustness of models to removing the deeper layers, the sharp transition in performance in downstream tasks, and the smooth behavior of the autoregressive loss with respect to these penalty fractions altogether suggest that the shallow layers may play a critical role in storing. So let me elaborate on all these things. Let's sort of unpack it. Now we know what the MMLU, and the bool queue are. One is question answer centered, and the other one is reading comprehension centered. So these are benchmarks, downstream knowledge tasks. and the smooth behavior of the autoregress. So what we notice, again, just to recap, this paper will find that you will have a situation like this, right? You can remove a lot of layers and still be fine up to a critical point. Beyond that, it does. Second thing you'll find is that healing works very well, and like you can heal it, and all of it suggests what? If I can remove some of the deeper layers, and you always take a layer, you find that in a, suppose X goes in and Y hat comes out, it is better to take layers out from here at the end, right? Except the softmax layer. Don't leave the last layer alone. Don't touch the last layer. Right? But everything except the last layer, start backing up from there, and you find that it is, you can get away by removing a lot. When you find that, what does it give you a clue? It means that the early layers, the shallow layers, play a critical role in storing knowledge, and the deeper layers are not as significant. That is the main message here. The structure of this paper is as follows. We first perform a literature review. It follows the standard. I won't go into it. So people have actually studied work. For example, one of the things people did in prior work was interesting. One study for bird style pre-training concluded that the best layer pruning strategies is dropping the final layers. So in bird models also, they found something similar. This partially resonates with our results. Although, in contrast, we find that for some pruning sizes, keeping the last few layers of the model is actually beneficial, right? Etc. So, there's some contradictory results, so some things are different. We'll leave that aside. They mention distillation and those things. I've covered all that. So let's come to the actual method. The actual method is quite simple. Let us say that, and this is the equation. Let's say that you have a layer. Suppose you have a layer. Why is this so fat? This or this. You have a layer. No, this is too thin. How about this? Suppose you have a layer L. Suppose X, the information that goes into this layer is XL, right? It goes in, and what comes out is XL plus Y, right? Now, you would agree that this layer internally, it is made up of some parameters, some weights and biases of this theta L. Right? Now, what they are saying is that if this layer is making any change, you can write that change as whatever change this layer made, you can think of it as whatever went in plus some function of the input and theta L. You could of course have said that this is just ideally, you see, you're just factoring this out. You're saying, let's take this part out, the input out from the total output, and what remains can be considered as a function of the input and whatever parameters that this layer is made up of. So I hope this looks pretty straightforward. The only thing it would differ from a more conventional way of saying it is, let this layer be function be G. Then you could have said XL plus 1 is equal to G XL theta L, right? The only difference is you break it up into, deliberately by choice, you break it up into G plus. That's all. You subtract. You can think of F as G minus the input. That's it. It's just a way of writing. Now, when you do this, and now the whole question is, what do they mean by this layer? They are very particular, and they say that the F theta describes the transformation of one multi-head attention and MLP blocks. So just to recap, if you remember, the way these things work is that you have multi-head attention stacks, right? And each of these will have the weight matrix transitions, KQV, right? The embedding goes in, and they will produce their KQVs, and then those results are synthesized and so on and so forth. And finally, you have some feed-forward layers or multi-layer perceptrons, like basically dense layers. So what they're saying, which is very conventional these days, to look at this entire thing as one layer, because then this thing repeats itself. You stack on top of each other, right? This thing goes through this, then it goes through. Well, actually, I should have broken it up into 3 different. Each will have its own feature. So anyway, all of those things happen. So they make a point that the F represents the action of the entire head with its attention part and its simple feed forward part also, MLP. That's what they're saying. As for any residual, now what happens is, you notice that this equation is recursive. If you look at this, if xl plus 1 is xl plus function xl theta l. Now, but xl is what? xl is xl minus 1 plus the same function, some other function, and well, let's say xl minus 1 theta l minus 1, right? And so on and so forth. So if you just work it out, it will just become this this equation, namely the output of any given layer is equal to the output from the first layer, the input basically, plus up to L minus 1, the action L minus 1, L is equal to 0 of x L theta L, right? Whatever the L value is. So you're iterating over L is equal to 0 to L minus 1. So they're just writing it, unrolling it or writing it out because of the recursive nature of this equation. So of course, they are not all independent. Now we do realize that the output of a given layer is not like independent of the output of the previous layer. That is a given, right? Whatever the previous layer produces becomes the input to this layer. And so the output from this layer is very sensitive to the output from the previous layer. And that is a given. But what they are saying is, what if this were true? What if we find that the XL of a given layer, the output of a given layer, is actually very close, to XL up to, so first let's say 1 layer plus epsilon. It is almost the same as the output from the previous layer. Suppose you could do that. What would it mean? It would mean, I hope that you see, that it would mean that this is small, very small error, very small perturbation, let's just call it. Then you would agree that this layer is acting as, layer L is acting as, then L is essentially just transmitting the information forward. Does that make sense, guys? It is just transmitting the information forward. Now we can generalize this. Why just one? What if we notice that not just one, but many layers are collectively doing the same thing? So suppose you have XL is almost the same as L minus N, like N layers before it all together seem to be doing nothing, right? Maybe this is too fast. N layers, they all seem to be doing the same thing. Then what would it mean? It would mean that you can basically take out those N layers, completely take out those N layers, isn't it? Now the thing is, how would you measure? How would you know that these things are almost the same? So you need some notion of distance or similarity between this and this. And the notion of distance or similarity that is perhaps the most common when you're dealing with high dimensional vector spaces, especially when which is very, very common when you're dealing with large language models, because the output of each layer is a very high dimensional vector. In high dimensional vector spaces, angular distances are very common. Angular distance is the common. What does it mean? Given two vectors, you look at what is the angle theta between them. So suppose I have a vector A and I have a vector B. What you do is you take vector A and vector B and you just, you say A divided by the magnitude of A, B divided by magnitude of B. If I take the dot product, A dot B, you realize that this is a little bit of basic vector calculus. This is the cosine theta. And therefore theta is equal to arc sine or cosine inverse of this quantity. This is also written as arc cosine, A over A, B, B over B, B over the magnitude, B, the dot product, and divided by the magnitude. Now it turns out that the angle will go from 0 to pi. So people, they just say that the distance between the two vector is distance is equal to theta over pi. They just normalize. It's very customary to normalize it so that you say distance between A and B is 1 over pi arc cosine over A dot B over A B magnitude. So when you look at this thing, which is a very common way of looking at distances, perhaps one of the most common ways of looking at distances at higher dimension space. And the basic intuition is, see, when you look up at the sky and you say, I see a star and I see a neighboring star. In reality, it's not neighboring. It just means that the angular distance between the two stars is very small and they look close to each other because of that. So it's the same intuition of the angular distance that you carry. So now when you look at this formula, 1 over pi arc cosine of two vectors, you bring that and now pay attention to this equation, which basically says, what is it that we are trying to do? We are trying to find the distance is defined as between the layer, this layer, and where this vector and this vector is just this, given by this equation. And I hope now this looks pretty simple to understand. So what they do is they just say, we are going to look at this network and find optimal cut points, what they call L star, such that if I have to cut n layers, what is a good point to cut such that XL star is more or less equal to XL or XL plus N is more or less the same as XL star, right? Up to a small amount, very, very small amount. What is the place where you have minimum distance? You minimize the distance. And so the criteria of cutting, they write it as, you find the L star such that where is the minimum distance, like the smallest difference between input and output, if I were to cut these layers out. Those would be great candidates to drop those layers. Now, you may say that, well, that looks rather dangerous. You're doing a pretty critical surgery on the neural network, and what does it lead to? And so the results that come out speak for themselves, actually. They're pretty remarkable. And they're there at the beginning of the paper itself, in the very first figure. And I'm going to blow this figure up and see, we'll go over it. So what it does is it keeps computing this layer by layer, and it says, hey, let's look at these layers, and we are going to cut out these layers. Right? We are going to remove it. And when you do that, then you can apply QLoRa and look at the healing and non-healing. Let's look at only one of the measures. This is one. Accuracy is the performance. The x-axis is the percentage of layers that you eliminate by this process. Do you realize that if we look very carefully at this picture, it is almost or maybe I'll use another color so that it begins to show. If you notice, where performance begins to drop. Oh, sorry. Less. Where performance begins to drop. It is almost at 40 to 50% of the layers. If you drop performance, the accuracy remains. If you notice this, accuracy remains more or less the same. In fact, when you do they've given you blue line, the light blue line is Llama 70 billion with healing, like with QLoRa, and the darker blue is no healing. So obviously healing is having a positive effect, right? It is giving you. Now, this orange line is, of course, the model without any of the layers taken out. And this gray line is the performance that would be there in a model that is hopeless, that is pretty much making random guesses. So what happens is, after you take a certain number of layers out, another interesting observation is that there's a catastrophic drop of accuracy. You know when to stop, because after that, catastrophically, you will start losing a lot of performance, right? And this is true on the other benchmark also, you notice, right? And you notice that here also, like when you look at the cross-validation loss, there is a whole region of like stability. You don't seem to lose much, right? And with healing, you seem to lose very little. Now, this picture is a little bit harder to interpret. So let me, this C picture, so I'll explain. So let's look at any one of these lines. These are increase end. Like how many layers should I take out? If you take out only 1 or 2 layers, no, this is not taking out layers. What is the angular distance? If you take only 1 layer, like let's say a small number of layers out, the number of layers is small. In the early stages, well, in the early stages, you can see, do you notice that these values are big? It means that in the early stages, each of the layer is doing something substantially different. It is applying quite a transformation to the input that it is getting. But progressively, as you go to deeper and deeper layers, you notice that it is all decreasing. And you can chop off many, many layers from the machine, right? That's the basic message. You see it curve down, and you see that essentially, the deeper you go into the layer number, the more you find that the angular distance is very small. You notice that the angular distance here is very, very small, right? Between the layers. So that's the main point they observe. This is a remarkable empirical observation. And the benchmarks, of course, speak for themselves. As we
Asif, I have, sorry, one question, maybe very naive to ask. So this experiment says, like, if we have a very deeper network, and at the last, there are few layers where the angular distance is less and they are not contributing much. So what if we just take a smaller model itself, which does not have so much of layer, because this experiment says so many layers do not contribute. So if the model itself does small and we have the less layer, and in this way these less number of layers will contribute more and have some kind of cascading or a LoRa itself while training. Since we are benchmarking and trying to fine tune something on this.
I got your point.
Yeah.
So the basic question is that, can we not have just trained a much smaller model, 50% done it? See, that is, I suppose, the area of future work, where the bottom line is that there is a neural scaling law. What it means is that you have to start with a slightly bigger model, because smaller models, they simply don't develop, or that they have the capacity to develop or learn or be able to do certain things. But once they have developed the ability to do certain things, what these people are saying is, once they have developed, and essentially you start with a bigger layer, somehow train it, then the earlier layers become pretty smart, and then there is some redundancy left behind, and you can chop off that redundancy. That's what they're saying.
Oh, okay, that makes sense. Thank you.
So accuracy on QA benchmarks, etc., etc. Now observe something very interesting. If you look at the cross-validation loss, when you don't do healing, you realize that the cross-validation losses, they begin, let me just focus on one of them, 70 billion parameter. This is the blue line, right? So if you just look at the blue line here, I lost track of where it went, but it is, let's say that it's somewhere around here, right? I just made the blue line into a black line just to emphasize that. You can see that the cross-validation loss, which is normalized on a log scale, does increase quite a bit. But when you do healing, now notice the scale. This is on a scale of 1 to 1.5, and this is on a scale of just 0.5. And in fact, the same blue line, which I'll color black, do you realize that it barely achieves a loss of between about 0.27 cross-validation loss, right? So this speaks to the fact that it is a good thing to do healing. Right? Now, there is more going on in this paper, but I think we have, and they represent the same information as a heat map, where they say that if you look at the angular distance, yellow is low, purple is high, right? So when you look at the layers, a layer number, let's look at 70 billion parameter, layer 80. What do you notice? Angular distances here, they are mostly yellow, isn't it? Block size. So you can chop off a lot of layers, up to 20 layers, and still the loss, the angular distance is very, very low if you skip off that, and therefore you can remove up to 20 layers. The same is not true if you take very small models. So it seems that, and this goes to the fact that Praveen, that you were saying, why not just start with a smaller model? Right? You have to start with sufficiently big models so you see this region where you can do the pruning. So that's an interesting thing. Now, your pruning strategy, healing, no healing, there's a lot of that going on, but it raises a lot of questions actually that they mention, and it's good that they leave a lot of unanswered questions. They ask, what are better layer pruning strategies? So they took a very simple strategy, which is just look at the angular distance. It is sort of, it is almost like a thought experiment. What if we remove some layers using a simple strategy? And they found remarkably that you can do it without loss of accuracy or without significant material loss of accuracy. So then the question it raises is, are there better approaches? Are there better approaches to healing other than QLoRa? So guys, if you have been following the history of the performance efficient fine tuning, the jury is out there. QLoRa is good, but you do lose some. And then people have often pointed out that in many, many cases, it is not satisfactory. You lose quite a bit in the accuracy. In some other situations, you don't lose as much. So obviously, quantization, LoRa adapters, as opposed to full model fine-tuning. These are all the different decisions to make and ask, do we have better things that we can do for healing? Why does healing eliminate the phase transition in the loss, but not in the QA accuracy? So you notice that in the loss, there's a sudden dip, like suddenly the thing fails, but in the accuracies, but not QA. So there's some interesting observations they make, empirical observations. The other question that they ask is very interesting. They played with only a few models and only a few benchmarks. So they asked this question, with more comprehensive evals, will accuracy on different tasks degrade at different depths? So in other words, we are saying, this paper is saying that the deeper layers are not very useful, but they don't know whether on some other task, the degradation happens in the early layers or the middle layers or somewhere. One would guess it doesn't, but obviously it needs more experimentation. Relatedly, is knowledge generally stored in shallow or middle layers, or is it delocalized? So it's one of the things that people have asked, that it is true for the human brain as well as for this. You can ask, where is the knowledge, a piece of knowledge stored? To the best of our knowledge, neuroscience says, is delocalized. It's sort of spread out and stored. And it seems that for neural networks also, people have done some studies and shown that when it remembers, when it stores the knowledge, it is not stored in one layer about one piece of information, but it is actually spread across layers, it's delocalized. So now the question is, relatedly, is knowledge generally stored in shallow or middle layers, or is it delocalized? Is it spread all over? All over, we don't know. Do pre-training details affect the ability to train? So in other words, yes, you're pruning, but a llama was trained in a particular way, and a few of these models, Phi, etc., were trained in a particular way. Is it true that if you pre-train the model in a different way, then what you're seeing here may not be seen anymore, right? So that's a question. Do pre-training details affect the ability to preen? Example, are scaling law overtrained or distill models more difficult to prove? So in other words, if you overtrain a model, the scaling law, of course, they're referring to the neural scaling law. And they ask this question that if you overtrain compared to the scaling law suggestion, then are they more difficult to prove? Or for example, if you distill a model, are they more difficult to prove? Those questions have to be answered with further research. And lastly, it asks the question, how can we LLMs to more effectively use the parameters in the deeper layer? So in other words, we seem to have somehow not been very effective at training the deeper layers. What is it that we need to do to properly train the, right? Or train the LLM so that all the deeper layer parameters also come in useful. So that was the paper reading. Any questions, guys? Anybody has a question? Was it reasonably clear?
Yes, much more clear than just reading it myself.
Thank you. So this is a straightforward paper with one message. It seems that the deeper layers are not doing much, and quite often you can prune them and therefore make smaller models. You prune and heal it, and then make smaller models. And because models spend most of their time in inference, most of the computation lifetime is spent in inference. Therefore, there are benefits to doing this. That seems to be the main message. Now, it raises deeper, so that's the practical message. And it leads to a lot of deeper scientific questions. And why is it that the deeper layers are not doing much, it seems? And how true is it? Is it an artifact of the way these models were trained, or is it something more more fundamental? Those questions are left out.
So, Asif, just a commentary on what you covered. Can you hear me?
Yes, I can hear you.
Okay. So I think I discussed with you also, right? Wolfram has been trying to look at these models, the layers quite deep, and try to analyze the weights as they go across. So his take has been that the initial ones are Gaussian, and then later on, the distribution of those weights are different. And what he's been saying is, depending on the different data sets or tasks that have been done, right? It's like human intuition, right? The math has a different reasoning, language has a different reasoning, and all of that reasoning basically happens at the subtle layers of the higher level layers. So I think with this paper, the LoRa, and also from the understanding of what Wolfram has been saying, when you try to do this on a particular domain, right, you need to have another data set by which you can compare and say, okay, this is kind of giving us better results in that domain, and then use it fine tune and then do the pruning and healing, right? Because you need to know that you haven't lost anything critical that is required for that domain, right? So you do that as an iterative exercise, and then I think this has quite a lot of promise. So that's one. The other reason is, do you know why they chose the A100? Is that like the de facto, what do you call, compute that will be required for all different, what do you call, science fields and things like that? Is that what would be starting unit?
A100, right, is a price performance wise, it is sort of a good balancing point. Think about it this way: 4090 is almost hopeless for these situations. Next level would be, what is it, RTX 6000, 48 GB. 48 GB is sort of, sometimes you get away with it, not. The basic rule has been that 80 GB, if you're loading a 70 billion parameter model, right, and you're doing LoRa, think about it this way: 70 billion parameter model, you need to quantize. If you these people quantize it down to 4 bits, right? So it means that 40 GB goes into quantization. I mean, the loading the model itself. That leaves you a little bit of another 40 GB to do just about everything else. Bring in your LoRa, its weights, its gradients, and everything. Right? So the minimum hardware needed to fit this experiment would be something that supports 80 GB. And that would happen to be a A100 because H100 would be more expensive and also hard to get these days. All of them are booked.
Thank you. So,
Any other questions, guys? All right, so I'm going to